Okay, so the second example, so it's still going to be the case of polynomial, but for this case, this is going to be slightly different from the first example. And I even purposely changed the variable for this case so that you can see the difference. Remember, when we write the solution for differential equation, so the dependent variable is going to be always on the left-hand side. Everything on the right-hand side should be in terms of the independent variable. For this case, everything should be in terms of y and t. There should be no x at all in your calculation because the only variables we had are y and also t. So now let's start finding the general solution of this. So this is a pretty simple equation. So we're going to start with yc. And for this case, my characteristic equation, this is going to be the only term that we have to change. I'm going to have m squared equals 0. And what happens is that this is going to be the case of equal roots for which m1 and m2, they are both going to equal 0. So if you factorize, your function is going to look like this. You're going to have m plus 2 square. Sorry, it's not going to be m plus 2 square. So it's going to be m plus 0 square, which is going to equal 0. So you will get equal roots of m1 equals 0 and m2 equal 0. So when we write down the solution, remember, our independent variable is going to be t. yc of t is going to equal a plus bt, exponential of 0t. And of course, we know the exponential of 0 is simply going to be 1. So therefore, our yc is going to be a plus bt. Right, so that is going to be the yc. So now let's move on to the second component, which is going to be yp. And for this case, our function f of t is given by 6t squared plus 2t plus 1. And now let's write the family of derivatives. The highest power of t is going to be t to the power of 2. Remember, neglect the constant, you don't need the 6. And the next element is going to be t, and the last element is going to be 1. And of course, you're going to multiply this by c, d, and e. And if you are afraid that your c could actually got mixed up between the bracket, so use something else, d, e, f, so that should be fine as well. For which now I can write that my yp of t is going to be given by ct squared plus dt plus e. And I did mention to you in the previous example, make it a habit. So the fact that after you have written your yp, straight away check for the condition that yc and yp must be linearly independent. Okay, now let's check for the linear dependency. So here, remember, this is not a by itself, it's actually a being multiplied by 1. So when I remove the a, I'll have 1 and t. And for the yp, I'll end up with a t squared, t, and also 1. Remember, that is e actually being multiplied by 1. And I'm going to start comparing them. And I saw issues over here because this is 1. This is also 1. This is t. This is also t. So what happened is that for this case, my yc and yp, they are equal. So they are linearly dependent. So what happened is that when these two are linearly dependent, so this cannot be your yp. So what do you have to do when you come across the case of being linearly dependent? So you have to change your yp. So how do you change your yp? So multiply yp so by the independent variable. So this is the rule until they are linearly independent. Okay, so maybe you have to multiply only once, maybe you have to multiply that twice, and so on until they are linearly independent. Okay, so therefore now what is my independent variable? So for this case, my independent variable is going to be t. So therefore, when I propose my new yp, so this is going to be my new yp. So I'm going to have yp of t is going to equal ct squared plus dt plus e. And I'm going to multiply this by the independent variable, which is going to be t. And I'll come up with a new one, which is going to be ct cubed plus dt squared plus et. And again, I have to check. If this one is already li and I'm going to stop, this is going to be my yp. Okay, and then when I remove the c, I'll get t cubed, t squared, and t. Okay, however, so we still have issues right here because let's make it smaller so we can have a look at both of them. So this is t and there is still a t term right here. So meaning by I have to do the same thing again. So therefore, this also cannot be the they are still equal, they are linearly dependent. So this also cannot be the, what do you call that? Cannot be our yp. So we have to come up with a new one. So how do I come up with a new one? So previously, I multiply by t to the power of 1. So now what I'm going to do is, I'm going to multiply my original yp, which is ct squared plus dt plus e. So I'm going to multiply it now by t to the power of 2. And of course, when I multiplied it by t squared, I'll end up with ct to the 4 plus dt cubed plus e t squared. And when I remove the c, d, and e, so this is going to be the function that I come out with. And of course, for this one, when I check for the linear dependency, so I noticed that I don't have any more problem because this is 1 and t, but none of these are 1 and t. So therefore, for this case, yes, none of them are the same. They are linearly independent. So to what extent are you going to do this? You're going to do this repeatedly until they are going to be linearly independent. So meaning by, at this stage, if they are already linearly independent, you just stop. But I have to proceed by multiplying by t squared because they are still linearly dependent. Okay, so therefore, yes, so this is going to be our yp. So the rule is that when they are linearly dependent, so multiply that by the independent variable. If you're using t, multiply by t. If your independent variable is x, multiplied by x. And I'm going to stay with the same step as previously. I'm going to have to differentiate this twice in order to find the value of c, d, and e. So my y prime for this case is going to be 4ct cubed plus 3dt squared and 2et. That is going to be the y prime. And y double prime, the second derivative, is going to be given by 12ct to the power of 2 and plus 6dt plus 2e. Okay, so that is going to be the y double prime. So now that I already have the first and the second derivative, now I can substitute back into the original equation. So my original equation is given by y double prime is equals 6t squared plus, what's the value? So this is just the equation from here, plus 2t plus 1. Okay, plus 2t plus 1. Okay, let's add another page. So when I substitute, I'll end up with, I only have to substitute for y double prime. So that is going to be 12ct to the power of 2 plus 6 dt plus 2e, and on the right hand side is going to be 6t squared plus 2t plus 1. So this is going to be a super simple comparison. Alright, first I'm going to start with comparing t to the power of 2, and on this side this is going to be the coefficient. So I'm going to write the fact that 12c is going to equal 6. So my value of c is going to equal 6 over 12, so that is going to equal a half. And then next preceding power, t to the power of 1. And for the case of t to the power of 1, my coefficient is given by 6d on the left, 2 on the right hand side. So therefore here I'm going to have 6d is going to equal 2. So my d value is going to equal 2 over 6, which is 1/3. And then the last one is going to be the constants. So concerning t to the power of 0, which I only have 2e is going to equal 1. So straight away we can tell that the e value is going to equal a half, 1 over 2. Right. So now that I already have all the values, so I have a half, 1/3, and a half. So what I'm going to do next is I'm going to substitute into the yp, and be careful. So bear in mind when you start substituting in the yp, so which yp are you going to substitute? You're going to substitute into the yp that is linearly independent for this case. So this is going to be your yp. This is the one that is linearly independent. Okay. So let me put over here. So your ypt is given by ct to the power of 4 plus dt to the power of 3 and plus et squared. No, it's not this one. It's this one, isn't it? Yeah, that's right. So that is going to be ct to the 4 plus et cubed plus this is d. That's an ugly d. So this is going to be dt cubed and et squared. Okay, so when I substitute value of c, d, and e, I'll end up with a half t to the 4 plus a t to the power of 3 and a half t to the power of 2. So we substitute into the yp that is linearly independent. So that's what you're going to do. And of course now, so the last step is we're going to write the general solution, which is yc. All you have to do is combine yc plus yp. And for this case, my yc plus yp is going to be given by a plus bt plus a half of t to the 4 plus a quarter t cubed plus a half of t squared. So that would be the outcome. And of course, for this case, there is no initial conditions given automatically, so we only stop until general solution. So that is going to be for this particular example. Okay, so that is going to be for the case of polynomial. And how do you handle when you come across the case of being linearly dependent? And for the next example, so I'm going to show you the case of exponential. So we have, remember, polynomial, exponential, sine and cosine. So out of all these three cases, exponential is going to be the easiest. One of the reason is because of the family of derivative. So there is only going to be one element in our family of derivative. So that is why it make it easier, and the calculation is going to be shorter as well. Okay, so now let's start with this particular example. So I'm going to start with the YC. So here my characteristic equation is going to be m squared plus 6m plus 10, and that is going to equal 0. And let me use your calculator, my calculator as well, because I figured out this is definitely going to be the case of complex root. So what is going to be the outcome for that? Okay, so if you use your calculator for that, you'll be able to figure out that your roots m is going to equal -3, so plus minus of I. And for this case, our alpha is going to be -3. Our beta value, that is going to equal 1. So therefore, I'm going to write that, what's my variable x? So I'm going to have yc of x is going to equal exponential of negative ax, which is a -3, multiplied by, so it's not a, it's alpha, multiplied by a cos of beta, which is going to equal 1. So I'm going to have 1x plus b sine of 1x as well. Okay, so that is going to be my function yc. That's it. You stop until there. That's your yc. And now we're going to proceed with the next element, which is going to be the yp. And for this case, our function f of x is given by this function right here, which is 2 exponential of -2x. And remember, for exponential cases, there's going to be one element which is going to be the exponential by itself. I remove the constant 2. So in here, I'm going to have exponential of -2x. And when I write down my yp, I'll end up with yp of x is going to equal, let's use d. So for example, d exponential of -2x. And of course, remember, what we have to do is we are going to write, after you've written your yp, so compare for linear dependency. So let me move this to the bottom, because we apparently have to expand this before we start comparing. Now when I expand this term, I'll end up with a exponential of -3x cos of x, and the second term is b exponential of -3x sine of x. Okay, and then only we start comparing. I remove the a, so this is what the function I end up with. Remove the b, that is going to be the outcome. I remove the d, this is going to be my function. And this is obviously going to be linearly independent. They're not equal. So linearly independent, this is going to be a yp, because obviously that's exponential of -3 cos, exponential of -3 sine, and this is just exponential by itself. So they are going to be linearly independent. Right, so I'm going to proceed to differentiating this twice. So my first derivative, y prime p, is going to be -2d exponential of -2x. And my second derivative, that will be given by 4d exponential of -2x. And now let's substitute this into the original equation. So I'm going to have y double prime plus 6y prime plus 10y, and that is going to equal 2 exponential of -2x. So y double prime, so that is going to equal 4d exponential of -2x plus 6, and do not forget about the constant at the outside. Y prime is going to be -2d exponential of -2x, and then I'm going to have plus a 10 of y, which is going to be d exponential of -2x, and that is going to equal 2 exponential of -2x. Okay, for the case of exponential, how do we make our calculation simpler? So there's the tips for that. So the tips of that is you factor out the exponential. So when I factor this out, so for the first term, I'll end up with 4d, and do not forget about multiplying this with the constant 6. You'll end up with -12d, and then I'm going to have plus 10 of d, and that is going to equal 2 exponential of -2x. And of course, if I were to simplify whatever that I had in there, I'll have 14 minus 12. That is going to equal 2. So I'm going to have exponential of -2x multiplied by 2d. and that is going to equal to exponential of negative 2x. So now it's going to be super easy to compare and find the value of d. So the coefficient on the left hand side is 2d, the coefficient on the right hand side is equal to, so straight away upon the comparison we can tell right away that 2d is going to equal 2, so my d value, that is going to equal 1. So that's my d value. So now that I already know my d value, I can substitute into my yp. So my yp of x is going to equal d, so which is going to be 1. So exponential of negative 2x, that's my yp. And of course my y of x is going to equal exponential of negative 3x. So multiplied by a cos of x plus b sine of x. So combine that with the yp, which is exponential of negative 2x. Okay, and if the question asks you for particular solution, so substitute and find the value of a and b.